What's up, everybody? So our focus for today's video is to look at, learn about, and apply, I guess, the conditions for sampling distributions. So here we go. So most recently, right, we've started to look at what a sampling distribution is. We've talked about this idea that a sampling distribution is a distribution of sample statistics taken from repeated samples, right? We're transitioning from a graph previously was just individual data values, like, one person's height, one person's age, whatever. But now we're starting to move to viewing a sampling distribution, which is a graph of sample statistics. Each point on the graph on the sampling distribution isn't just one person's height or one person's age. It's take a sample of 10 people, find the average age, plot it, right? So sampling distribution is this idea that we're going to take a random sample, find some sample statistic, and plot it, right? And in our course in AP Stats, we're going to focus primarily on the sampling distribution for means. Take a sample, find the mean, plot it, take a sample, find the mean, plot it, and repeat theoretically an infinite number of times. And we're going to focus on sampling distributions for proportions. And so as we started to dive into this, we were playing with these applets, right? And we saw that the sampling distributions became approximately normal, which is going to lead to a bunch of math, right? We're going to connect to what we know about the empirical rule and the normal model. But it turns out that really for the sampling distribution to become that normal model and for us to then implement all the mathematical techniques we're going to implement, especially as we start to build confidence intervals and conduct hypothesis tests, certain conditions have to be met. Now, this is weird to us. In math class, we've never had problems before where we first had to verify certain conditions were met to use some mathematical technique. That's what's going to happen in here. So as we move forward, before we do a sampling distribution free response, or before we create a confidence interval coming in the next unit, or before, well, the rest of the units really, or before we start a hypothesis test in our future units, we are going to have to check that certain conditions are met. So this is step one of a free response. So we can't gloss over this. So checking conditions. There are three conditions to check. Two of them are the same, but the third one differs depending on the type of the sampling distribution. So we've got sampling distributions for means. That's when we're working with quantitative data, right? Taking sample, find some quantitative variable, find the average, plot it. But of course, like the word means probably going to be in the context, so that should give it away. A sampling distribution for proportions. Remember, proportion is just a fancy word for percent, is when we're working with categorical data. But again, right, the context, like there's going to be percentages probably referenced, so that should make it obvious. Now, regardless which of the two we're using, whether we're talking means or proportions, the first two conditions are the same. So I'll write them in the middle. So we'll start by just listing what the three conditions are for each type of sampling distribution. Then we'll go through and talk about each condition more specifically, and then we'll look at two examples to wrap up. So the first thing is we always want a random, or in other words, a representative sample. We want our data to be collected the right way. That shouldn't surprise us. The reason, and again, I'm writing this in green in the middle, is that applies to both of these. Whether you're talking about means or proportions, we always want a random or representative sample. The next thing we're going to talk about is something called the 10% condition. Our sample has to be less than 10% of the size of the population. And similarly, we check that condition regardless of the type of sampling distribution that we are working with. Right? So for every interval and test for the rest of the year, for both of these types of sampling distributions, we're always checking for a random representative sample, and we're always checking this 10% condition. The third condition is going to differ based on the type of sampling distribution. If you have a sampling distribution for proportions, for percentages, we're going to check what our book calls the success failure condition. Now, another thing that's important for me to note is it's not the name that's relevant. So when we go to check these conditions, you can't just write like random, check mark, success failure, check mark, right? That garbage gets 0 points. So it's not really the name of the condition that's important. It's how you check it that's important. This condition, we're going to do n times p has to be bigger than 10, and n times 1 minus p has to be bigger than 10. We'll talk more about that when we get to that slide. But if we're talking about a sampling distribution for means, we cannot check this condition because P stands for a percentage, and we don't have percentages if we're working with means. So if we're talking about a sampling distribution for means, we're going to check what our book calls the large enough sample condition. Which means we want a large sample, or our sample data has to be approximately normal. And that information will be written on the screen when I get to that slide, so I'm not going to write it again here. So regardless of what type of sampling distribution, or later in the year, what type of interval or test we're using, there are going to be 3 conditions to check. No matter what, random 10%. And then the third condition, right, we kind of split, depends on the type of sampling distribution being used. So moving on. So random sample, like it pretty much is what it sounds like. To check this, you're going to have to look at the context, right? This information would have to be given in the context. There's no way you can mathematically figure out if you have a random sample. On the AP exam, a free response is going to tell you it's a random sample. Or if we were looking at some real life study, we would want to look at the method of data collection and see if it's a random sample. Like if they tell us it's a voluntary response sample or a convenience sample, then we know it's not random, right? So we fail this condition. And why we check this, why we want a random sample, is because we want to feel confident that our sample is representative of the population. Or in other words, it's not biased. And typically, right, of course, a random sample could lead to some bias, but on average, random samples do a pretty decent job of avoiding over or underrepresenting any particular group. So that's why we want a random sample. So we feel like we have reliable representative data. Now, how do we check that? Again, we do not do this. Some of you guys are going to do it anyways, and then I'm going to give you a 0, draw like an angry face or something. We got to write a little bit in context. Our sample of blank was collected at random. This is just going to be what your sample is in context. So if it tells us in the question we have a random sample, which is what will happen on an AP free response, our sample of 50 East Harvard High School students was collected at random. Our sample of whatever, 5,000 automobiles was collected at random. That's it. Don't be lazy like this person. Or I might give you guys some homework examples. You'll see one in this slideshow where it doesn't tell us that we have a representative sample or a random sample. So for now, we'll have to assume that our sample of whatever's is representative or was collected randomly. That's not going to happen on the AP exam, but you might see that happen if we start to look at some real things that I, pull offline or whatever, or from the textbook. So again, right, this is going to happen more often. This assumption, we might have to make this assumption occasionally. Randomization is a pretty easy one. It's just, read stuff, have eyes. The 10% condition. So the 10% condition says our sample size has to be less than 10% of the population size. And jumping to the bottom, the way we check that is we're literally going to say our sample of whatever, define our sample in context. I don't know why I didn't space out those words, but I'm not going to fix it, is probably less than 10% of the population in context. So a couple things here, right? We're not going to write 10% check mark. Don't do that. We're going to write this phrase. So a couple things I want to point out. This likely. In a lot of situations, we don't really know the exact size of the population, so we kind of have to assume that our sample is less than 10% of the population size. In many cases, that's a very reasonable assumption. You can just get in the habit of putting that likely in parentheses to be safe if you want to. Every now and then we'll be given the population size, so we could mathematically check this condition, but that's less common. The other thing is, notice you have to be able to identify the sample and the population in words just to check this condition. Right? So something that previously maybe I had separate quiz questions that are what's the sample, what's the population, that's all now just built into this one condition. The why for the 10% condition is the trickiest of all of them. For now, I'm going to do my least favorite thing as a teacher and just tell you to take my word for it. So we check this 10% condition to assume independence within our sample. That probably is a meaningless statement right now. So, I guess just write it down and remember it for now. When we have time, we'll dive more into that. But in the interest of not making this video 46 hours long, I'll hold off on that. But or Google it and then share with your results with me. Maybe it's a better explanation than I would give. So that's the 10% condition. And we'll see that in action in a couple slides. So lastly is where it becomes the most complex because the condition differs depending on the type of sampling distribution. Sorry, I just wanted to see what color I used for proportions. So random and 10% apply regardless of the type. Let's start over here with proportions. If we have a sampling distribution for proportions, the third condition we check is this success failure. So we're going to actually do math. We're going to plug in numbers. We're going to do our sample size times P, that has to be bigger than 10, and our sample size times 1 minus P, right? We're going to plug in that number, has to be bigger than 10. Not all books use 10. Some books use 5 here. There's not like a unanimous definition of this condition yet. I'm not going to stress about it. We'll go with 10. Our book uses 10. But like, so if yours comes out to be 9, it's like, whatever. It's not that big of a deal. That probably won't happen. The other thing you need to know, P is that population percent. Hopefully we know that. That'll have to be given to us in the question. And we know that N is our sample size. I'm not going to write that down. So this is mathematical, right? There's no sentence to write here. We're just going to show this multiplication and make sure these values are bigger than 10. The reason we check this condition is to make sure N is large enough. And specifically, when we say large enough, it's large enough that the sampling distribution is going to be approximately normal. So if our sample size is not big enough, the sampling distribution would not necessarily follow a normal model, and then everything we're going to do mathematically falls apart. So we have to make sure these conditions are met. That's what allows us to believe the sampling distribution is approximately normal, which is what allows us to proceed mathematically with all the stuff we're going to learn coming up in the coming days and weeks and months. Go back to the applet and play with it. Plug in an N and a P where this condition would fail and create the sampling distribution in that Reese's Pieces applet and see what happens. Now, if we have a sampling distribution for means, which I think I did in red, then we have to check that our sample is large enough differently. Like as I mentioned earlier, we can't do N times P. So I just made some of you puke with all those screen changes. We can't check this condition in blue for means because there's no P. There's no percentage. We're not talking about proportions. We're talking about averages. So there are a few ways this could happen. We'll start with the best case scenario. The best case scenario is you're just given a really big sample size. There's no definition of what's large enough. I'll even change this right now. Like bigger than 20, we'll call large enough. Again, there's no concrete definition of what's large enough. If you have a big sample size, bigger than 20-ish, you're just going to tell me our sample of 37 trees is large enough. Our sample of 500 East Hartford residents is large enough. This is what we hope happens on the AP exam because that's the easiest way to check this condition. However, if you have a small sample, right? So if N is smaller, and by smaller, I mean not 20-ish, right? Maybe your sample size is 15, or more realistically on the AP exam, you're going to be given a data set. Maybe we're given 15 data values. We have to check that our sample is unimodal and symmetric. And we can't just say it, we have to actually create a histogram. So this is the most time-consuming way we might have to check this condition. Maybe we're given the actual data set, got to pop all the numbers in L1, flash back to unit 1, create a quick histogram on our calculator, and make sure that the distribution of the sample data is unimodal and symmetric. This isn't going to happen, this red situation, for a little while. I'll wait till we get into unit 7 with t-intervals and t-tests for means. In the near future, it's going to be this kind of easier version. But, you know, of course, we'll practice this as we get closer, you know, whatever, deeper into this stuff. And it'll be a good way to review how to make histograms and all that. The third possibility is that they tell you in the context that the population is a normal distribution. That's probably the least common occurrence from what I've seen on the AP free response. I would expect it to be one of these two boxes, right? And that's what we'll see more commonly. So the third condition kind of has the most that goes into it because not only do you have to know which one to check, whether it's means or proportions, but then if it's means, there are multiple ways you might check this large enough sample condition. And again, lastly, when we say large enough, we mean large enough to assume that the sampling distribution will become a normal model. Because that sampling distribution being a normal model is the key to all of the mathematical formulas and procedures we're going to use with statistical inference, confidence intervals, and hypothesis tests. Before we get an example, to pass, all three conditions have to pass. If any one condition fails, then the sampling distribution's not appropriate. So occasionally, like on your homework, you'll have a question that says, explain why the sampling distribution for means is not appropriate. That means one of the means conditions fails. You just got to tell me which one fails. All right, 2 examples. Let's do it. Let's get out of here. So pause the video and try to check the conditions for this context on your own. We've got information on a packet of seeds. They claim the germination rate is 92%. That's our P. It says seeds are sold in packets containing 220 seeds. That's our N. We need to verify the conditions for a sampling distribution for proportions are met. This is usually not going to be here as part of the question. Usually it's going to be our responsibility to know that we have to check the conditions. So let's do that. Right off the bat, it never says in this context that this is a random sample. That is not going to happen on the AP exam. It's going to say random sample, but for now, we'll assume this is and you could say we'll assume it's a random, or you could assume it's representative sample of 220 seeds. We want some context, right? No random check mark garbage. Right, that seems fairly reasonable. It doesn't seem crazy to assume that this one packet is a representative sample of all the seeds of this type. So there's our first condition. The next thing is our sample has to be less than 10% of our population. And I think in this case, it's pretty reasonable to assume that our sample of 220 seeds is probably less than 10% of all seeds. Now, not all seeds of any kind in the world, but all seeds of this type. Maybe this is a packet of tomato seeds, so the population would be all tomato seeds, not, every kind of seed ever in history. We don't really know what the total number of all seeds are of this type, but 220 is probably less than 10% of that. There's probably more than 2,200 seeds of this type. Now, the third condition, right, this is where we differ. We have to think, is it means or proportions? Hopefully, obviously proportions, since we have some percentages right here, or a percentage. And so now we check our success failure condition. So N, which is 220, times our P, which is 0.92, has to be bigger than 10. And 220 times 0.08, remember this is 1 minus P or 1 minus 0.92, has to be bigger than 10. Now, like over here, like 92% of 220 is definitely bigger than 10. I don't even need to multiply that. I know 92% of 220 is bigger than 10. Here I am just going to use a check mark. Over here, maybe I'm a little less confident. Maybe, whatever. Maybe I can't do that mental math. So then I actually check, right? And that's what you're seeing here. All right, so 220 times 0.08 is 17.6, which is in fact bigger than 10. So that condition is met. When you're showing your work, as long as you have this, you'd be fine, right? You don't necessarily have to write the 17.6, but if it's close, right, check. The other thing I'll add is, if this is 17.6, this is our number of failures. Remember, that's a generic term connecting to our binomial probability. Then this, our number of successes, I could figure out would have to be 202.4. And I am not doing 220 times 0.92 in my head. Think about that. If this is 17.6, 220 times 0.08, how do I know that this product has to be 202.4? Think about that sometime. That's all extra. So we're assuming we have a random or representative sample. 220 is less than 10% of all seeds of this kind. Success failure condition passed. The last thing we want to do is we always want to name the sampling distribution. So there's 2 ways you could do that. You could do that at the end. So we could say now a sampling distribution for proportions is appropriate. That's why we're checking these conditions, to make sure we can use the sampling distribution, for proportions is appropriate to use, or is appropriate, right? That's why the conditions have to be checked, to make sure we can use this. Or you could name the sampling distribution at the top as like a title. I'll do that on the next slide to show you what I mean. So when I'm scoring this, I'm looking for randomization condition in context, 10% condition in context, success failure condition with the correct numbers substituted, name of the sampling distribution. So that's it. So all writing. A tiny bit of math, not all writing. One more. You know the deal. Pause it and check them yourself. So this time we have a sampling distribution for means, which is hopefully immediately obvious. So we've got human gestation times with mean of 266 days, standard deviation of 16 days. We're going to look at average gestation times for a random sample of 100 women. We want to see if a sampling distribution for means is appropriate. So this time, instead of naming the sampling distribution at the end, saying a sampling distribution for means is appropriate, I'll just have it as my title, sampling distribution for means. Personally, this is what I prefer to do because I know I would forget to name it at the end. So I like to put that as a title at the top and then underneath check the conditions. This time, we know it's a random sample, right? It tells us it's underlined right there in yellow. So this is a random sample of 100 women. Just don't be lazy. Don't write random check mark, right? Give me some context. It's probably true. 100 women is probably, it is less than 10% of blank. Remember, here we have to define our sample and our population. So in this context, we're saying our sample size of 100 women is likely less than 10% of all women. Maybe here, right, if we're looking at, well, I guess maybe they're not pregnant yet. Maybe they're going to get pregnant in the future. I don't know. So we can call them. What I was thinking of, would you say 100 pregnant women is less than 10% of all pregnant women here? I think I would mark that correct as well. I don't think it's really clear based on the context I chose. And then the third thing, so we got our random sample, nice and easy. It told us that. Hundreds, less than 10% of all women, no big deal. That's a totally reasonable assumption. There's way more than 1,000 women wherever we are. Can't check success failure, right? We're not in proportions. And again, hopefully we realize that would be impossible. It would be impossible to do n times p bigger than 10 because there's no p, there's no percentage. So here we check that large enough sample. And this is that best case scenario where we just have a large sample. So we're just going to say a sample of 100 women is large enough. There's no way we could check a histogram or anything because we don't have any data. It doesn't say anything about the shape, so they kind of just have to tell us that we have a large enough sample. And so here we go, and this highlighted stuff has a perfect score for checking the conditions. Well, now it is. When I highlighted it, the context disappeared for the 100 women in the album. Whatever. Shut up. All right, that's it. You'll have some homework in Google Classroom, and then the end. Have a wonderful day. This stuff is like really, really important. Watch this video 5 times. You're gonna have to check these conditions to start every interval or test for the rest of the year.